So we can see the effect of our three parameters of temperature, pressure, and water flow rate, but these parameters are correlated. So we would like to find a set of parameters that gives us the desired clean biogas concentration of 98% of methane. So instead of trying on a trial and error procedure these three parameters, there's a nice tool in ChemCAD, the sensitivity analysis, where we can change the number of parameters or the several values for these parameters. So we go to the screen analysis, and here we have the sensitivity. We set up a first sensitivity study. So let's start with two parameters because it's easier to see the effect of two parameters. Three are quite hard to visualize. So we select temperature and pressure. And in this screen, we can specify our parameters now. So our first independent variable should be the temperature in the flash unit. So we select here unit 1, type is unit op, and the variable in the flash is the parameter 1, which is the temperature. Here we can decide how we would like to specify this. So I prefer the linear step size. So we start at, for example, at 1 degree Celsius. We cannot go much lower with water because we'll start to freeze, and perhaps go to 20 degrees Celsius with a step size of 1 Celsius, which gives us 20 data points to be calculated. And then we add another independent variable, which is the pressure. This is the parameter 2 in unit of 1. And we can start it from 1 bar up to perhaps 50 bar. I'd like to use the step size again, so let's do this with steps of 1 bar. And these points multiply with each other. So now we have an overall of 1000 data points to be calculated, which will show us which biogas purity we can reach. Now, there are many variables calculated, so we have to decide which of them we would like to record. These are the dependent variables. So what we are looking at currently is the methane purity, so the mole fraction of methane in our stream. So from type we select now stream. In our stream number 3, the clean biogas, and here we select component mole fraction of methane. So now the flow sheet will calculate for 1000 times and look at the result, the component mole fraction of methane. But this, the sensitivity study is specified. Now we can here run all. We see these 1000 calculations are done still in less than a second. And we can look at the results here at plot results. We have 2 dimensions, so a 3-dimensional plot. We can plot this as a surface. If we remove here the 2D projection, we put on the X the temperature, on the Y the pressure, and the result should be the methane concentration. So if we use this, we can create this plot, and we see here which concentrations we can reach in a nice 3-dimensional plot. But results can be seen better in 2D projections, so we will do another plot while we do like a line chart in a 2D projection. And we see perhaps I should use a different way, because now I have here as a parameter the pressure, so we have quite a lot of points here. I will easily create another chart and switch X and Y. So I put the pressure here and the temperature as a line parameter. And this shows us the effect of our 2 parameters, temperature and pressure, on the methane purity. So we can see the effect of pressure is much larger, because by increasing the pressure, we remove more and more carbon dioxide and reach a higher and higher purity of methane. But we see that the effect in the beginning, it's quite high. but then it gets lower. On the other hand, we see the spread of these curves by the temperature. So the effect of temperature is by far not that large. And we see that also at higher pressures, the effect of temperature becomes smaller. On the other hand, we also see we are not reaching our 98%. The graph converges to a concentration of slightly above 95%. Well, we have another parameter we can play with, which is the water flow rate. So perhaps we can increase the water flow rate as a third parameter and then try to reach our desired 98%. At this point, perhaps I should have done this before. I'm still working here with a non-saved simulation. So I will save my simulation, give it a name. 0.2 we are looking at. And with this, our simulation is saved. So if some problem occurs, we can easily load it again. Now I want to add my third parameter. So I copy the sensitivity analysis and add T and P and the water flow rate F. So here's my copy of the sensitivity study, and I add an additional parameter, an independent variable, which is the water flow rate. So this is my stream number 1, the water. And what I'm going to change is the standard liquid volume rate. So we tested at around 100. So let's start with 100 and go to perhaps 500. And let's do this with a step size of 50. And we see we get 9,000 data points with this, which should still easily be handleable. And we run the simulation. And now it took a second to get the results. But now, unfortunately, we cannot easily look at the results in a plot anymore because we have 3 independent dimensions. So one option that ChemCAD gives here is the bar chart, where we can select the result of an independent variable. So the methane concentration, and here we can see the results, and we see the maximum methane concentration that we reach is 96.26%. So even with changing all parameters, we cannot get to the 98%. Well, this is still a sensitivity, so perhaps we did not find the optimal point yet. Can also have a look in a different way on this, which is the scatter chart. We can see the effect of one parameter, so we can look at the effect of the temperature, which is this chart. We can look at the effect of the pressure. Gives us this chart where we see how the pressure affects our purity. And we can see the isolated effect of the water flow rate, which is this chart, so where we see how increasing the water flow rate gives us higher concentrations, but the overall effect is not that big. This is the sensitivity study, so we still cannot reach our 98% and have to find out what we can do next.